Hello everyone, welcome to the video on portfolio management. So in this video, we're going to talk about two parts that are often involved in portfolio management. So first one is the prediction part, where we need to predict the price of the assets prediction. And then the second part is the optimization. This is where we optimize over the decision variables in terms of how much weightage we assign to each asset. So let's start from the basics. So assume we have an asset and we can say this is a stock, right? So we can see this is ST to denote the stock price at time period T, right? So if we draw a time series, then it's going to be, for example, something like this. So along the x-axis will be time, and then this will be the price S, right? So it can be go up and down, and then based on price, we can next calculate the return. So usually we do not look at the price directly; we look at the return in terms of how good or bad in terms of performance. So when we calculate the return at time period T, we look at the current period price minus the previous period, and then divided by the previous period. So this is the percentage increase in the price itself, right? We usually call it the simple return, right? So this is for this asset. We can use the simple return to characterize the performance at this period, right? So the problem of portfolio management is that now we have multiple assets, right? So asset A, asset B. So now in order to move into more assets, we can use, for example, R1 and R2, right? So use a vector all due to Rn. So assume we have n assets, right? So now we have n assets. And then I'm sort of ignoring the subscript T. So in fact, this is for period T, right? So this is to show that at this period T, right? And then we can observe this vector of returns as a returns because of n assets then as n returns, right? So but for simplicity, let's just ignore the subscript time period T for now, right? So just to know that every period we observe this vector of returns. So the next thing to note is that all these are actually random variables, right? So for example, this one, we can model it as a random variable, right? And then if it's random variable, that means it's not fixed, it changes, right? So it's a moving quantity, and it can be higher or lower than the previous one, and then it follows some distribution. So usually we model it as normally distributed. So that's sort of slight technical detail, which is that we actually model the log returns, which means that we actually take a log and then put it here. But we're sort of also jumping over these details for now. So for now, we need to know that each of them is a random variable, and they need to be forecasted in order to do optimization, right? So this is where prediction comes in. So when we run the optimization in terms of what is the optimal weightage we assign to each of them. So let's put another, which is W1, W2, all the way to Wn, right? So this is my decision problem, right? This is where optimization comes in. So this one is saying that I'm assigning W1 to asset 1. So this could be 0.1, 0.2, 0.2, etc. Right? So all this needs to sum to 1, right? Sum to 1 because assuming that I'm fully invested in the portfolio. So this typical constraint, which is that all of them should sum to 1, and that if I do not allow shorting, right? I cannot borrow the assets from others, then this weight also needs to be positive or 0, right? So this is another constraint commonly used if we do not allow shorting. So this is just one constraint, but in the end result is that we need to come up with this vector so that we can move forward with what allocation decision we make for each of them, right? So this is our decision variable. So in order to go from here to here, to go from the returns to the decision, then we need to do two things. So first thing is we need to predict, right? This is where prediction comes in. So we need to predict what are the expected returns for each of them, right? So the reason is because we cannot observe the future returns for each of the assets. So in order to calculate the objective of the optimization function, which we'll talk about later, we need the forecast for the returns. And let us be more specific about first what I'm trying to do, right? So the sort of objective function, right? So optimization function. So the objective, right? So objective. So what do we want to do, right? So in the problem of portfolio management, there are two things we care about. So one is the return, right? So return or reward, right? So return and one is the risk. So when it comes to return, then so both at portfolio level, right? So return plus risk at portfolio level. Now we have n assets, right? How do we aggregate to the portfolio level in terms of return risk? So for the return part, right? Return, we have the individual returns, right? We have the individual weights. Now the a natural way to calculate the portfolio level return is just to multiply each weight with the return and then sum it up, right? So I goes from 1 to n. So this to see that I'm just using a weighted average to calculate the portfolio level return, right? So this is how I calculate the return. And we can also write as W as a sort of vector form, and then transpose times R, both vectors, right? And then so this is portfolio level return. We want to maximize it. So this one to max, right? We want to maximize it. For the risk, so when risk comes in, we first need to calculate the covariance matrix. So the covariance matrix sigma describes the correlation between each pair of assets, right? So it's going to be a big matrix where so this 1 all the way to n, also this is 1 all the way to n, and then each element, for example, tells us what is the sort of co-movement between two assets, right? So of course, the diagonal entries are the variance of the assets themselves, and then the off-diagonal parts describe the correlation or covariance between different assets, right? So between different assets, we just use this sigma to denote the covariance metric of this portfolio. So covariance metric come in, and then because there are weights allocated to each asset, so the way we calculate the portfolio level risk or variance will be this. So we have this vector comes in, transpose, and then W as well. So this is another number that describes the risk at portfolio level, right? So we have these two objectives, and we want to minimize. This guy, right? So so we have two objectives. One is maximize, one is minimize risk. So typically we combine them together using like this. So let me just remove some parts. So this is our return, and this is our risk. We usually do weightage between these two objectives. So this we time this another another scalar, right? So this another parameter called lambda, and then we just minus it off, right? So because risk comes in, want to minimize it, then comes because the whole thing, the portfolio variance can only be positive. There's another positive constant, then we minus it. So we want to minimize this guy. And the whole term we want to maximize. So we want to maximize the risk-adjusted return. So this is risk adjustment, and this is return. We want to maximize it. and then maximize over this W as a decision variable. Right? So we want to find this W such that this whole term is maximized. So this is our objective, and this is also called mean variance optimization. Right? So that's mean, that's a variance optimization, which is initially proposed by Markowitz, and then so this is quite widely used in terms of portfolio management. Right. So here this is our final objective, and to do this, right, to calculate this quantity, we know that W is our variable we want to change, such that this whole term is maximized. But there are two terms that needs to be fixed. So one is this R, which describes essentially the expected return of the individual assets, and one is the covariance matrix. Right. So when we run this, in fact, in reality, we do not have access to these two terms because this represents future expected return and covariance. Right. So what do? We instead use another forecast. So we use H. It means that these are forecasted quantities. Right. So R is the forecasted, and sigma also needs to be forecasted. So this is where prediction comes in. So first we predict the expected return, and in fact, it's actually better to write it as the mu, right? So this is just representing that this is expected return mu. So R is itself is a random variable, right? So R, for example, first asset R is a random variable, and its expected the return is this expectation, right, of this random variable. And then how about the variance? So the variance is just the var of this random variable, right? So we have these two quantities that can capture which are essentially the first two moments, right? First moment is the mean, the second moment is the variance. So these two terms needs to be forecasted and go in here. So this is a vector of expected returns for individual assets. This is the covariance matrix, right? That again sits on the sigma as well as the correlation between different assets. So to sum up, first we need to predict the expected. So these two terms, right, expected return, and this actually goes into the sigma H, right? So this we are going to the mu H. So these two terms we need to predict. Once they are predicted, then they're fixed, right? So once they're fixed, then they come in here into NVO formulation, and then we do the optimization to run over search over different values of W, and then I propose the best W such that this whole term is maximized. Right? So this is our two-stage problem. So first stage, do the prediction for the asset returns and covariance metrics. Second stage, do the optimization to look at the optimum portfolio choice. And so of course, you can see that these two stages are discrete, right? They are separate. So meaning we need to do prediction first without knowing what we're going to do next, right? So this is actually separate. So first predict, then using the fixed prediction, right? They stay fixed. Then they move into optimization. Of course, we have no foresight in terms of how good or bad the optimization is when we do prediction. So that's a separate research direction called SPO, so which stands for Smart, Predict, then Optimize. Right. So previously we described predict and optimize. So these are two stages, but then this was the Smart comes. So Smart means that we are going to do prediction and optimization at the same time, right? So in one shot. So for example, we have some inputs, right? So this could be what we observe in terms of historical prices. Right? This is where prediction comes. So we observe that, right? Then we make predictions for mu H and sigma H, right? So this is the prediction problem. So input X comes in, and then we have prediction for these two terms, mu H and sigma H. And then this goes into optimization, right? This optimization where we have the optimum W here. So let's do this. Based on the prediction, we have the W star, right? This is the predict part, this is the optimized part. And then, so if we lay it out as a single stage, then we can essentially look at how good is this optimization. So we have some error terms, right? So in terms of if we compare it with the real mu and real sigma, so there's some error here and error feedback to here, right? Essentially, our prediction is on some set of parameters. Let's use it as theta, right? So now we come back to optimize theta such that the decision error, so let's call it decision error or optimization error, right, is minimized. So we are fine-tuning our forecast such that the decision is optimal, right? So we are not trying to do a good prediction anymore. We are trying to predict such that the decision is optimal. So this is exciting research area and something to think about because it sort of combines this two-stage problem into one stage. All right, so that's it for this video, and thanks for watching.